Hey, welcome everybody to our last week of BST 322. So again, Dr. Myers coming to you from San Diego. Again, this week, I'm going to do what I did the weeks before. I'm going to go through some of these slides for you. I'm going to lecture a little bit, but I'm going to try to, like I've done the other weeks, to jump in and do some analyses for you, some examples for the discussion questions, the assignment this week. Again, there's no quiz this week. We're going to do a final exam. The final exam, I take the quiz questions, I reword them and put them on the final. So it'll cover all weeks of the course, the final exam. It's 2 hours, so make sure you've got some time set aside, 50 questions. Again, have your textbook ready, your lecture notes ready. And for the final, you have 2 hours for 50 questions for that exam. And then the independent project, I'm going to talk more about that tonight as well. This week, we're ending up with correlation and regression. We're going to cover that tonight. We're spending most of our time on chapter 9, which is the simple regression and correlation. I'm going to talk a little bit later about multiple regression and some other types of tests. So we're making our way down. If we have that little cheat sheet here that's in course resources for you, we've been looking at the one with the charts and the tables. So we've done most of the parametrics in this course, and we did non-parametrics last week. And we're going to end up with our correlation, which we're going to use as a hypothesis test tonight. So we've done most of these tests, and then the ones that are left are at the bottom here, are multivariate. In this course, we're not going to do these tests. These are really high-level tests. You can take those in a graduate statistics course once you go on to graduate school, or if you take more stat courses. But I will be talking briefly about these at the end tonight, but these are multiple variables. 3, 4, 5 variables being analyzed. And again, in this course, we're sticking to bivariate analysis, right? Just 2 variables at a time. The only exception we've had is our two-way ANOVA that we talked about in week 2. But for the most part, right, we've been doing bivariate analyses here. So correlation, this is sort of a review. I'm like a broken record, right? We started this in week 2, and most everyone is getting this by now. So we're looking for statistical significance. We're looking at a test statistic, and we're doing a couple things, right? We're either going to look it up in the back of the book in a table, right? Compare our test statistic to the table value, typically at 5%, which we learned we made up. We live with 5% chance. Or we look at the p-value and we compare that to 0.05. As the test statistic gets larger, right, the probability gets smaller and smaller that we would see that in our data. The chance gets less and less. So this gets larger, this gets smaller. The test statistic, remember, and the probability value are related, but they're not the same thing. Okay, so we're always testing the null hypothesis that nothing's going on. And again, significance is if that p-value drops below 0.05, right, 5%, or if that test statistic is larger than a critical value, then we can reject the null hypothesis. We have a significant result. We do that with a significant result. We reject our null hypothesis. We accept the alternative hypothesis that something's going on. So we're going to do that same thing with correlation and our R value. And this is review because we worked on this in week 1, remember, with our descriptive statistics. We did scatter plots and correlation. So a bit of this is a review, right? So our sample data, we calculate R, or the correlation from, right? And remember, we get that very easily from StatCrunch on the Stat tab. StatCrunch will give us the correlation value. The population value of R is often called rho, so the lowercase Greek r. And that's what we're going to be comparing for this week for correlation. As we look here, it's very easy, right? We hit summary stats, correlation, and we can plot using scatter plot that we learned in week 1. And I'll go through some examples of this in just a bit for you, and it'll ring a bell, hopefully. So we talked about correlation, or Pearson's R, because Pearson was the guy who came up with most of these analyses, and it's a descriptive index, so we did it in week 1. It tells us the direction of the correlation between 2 variables, again, bivariate analysis. And now we're going to use it to make an inference about the population. Now we started with our probability in week 2. So go ahead and type in or turn your mic on if you're brave. A, B, or C, what's our null hypothesis going to be tonight for our correlation? Is correlation going to be A, it'll be equal to 0, there's no relationship. B, not equal to 0, there is a relationship, or 0.5, weak relationship. What's our R value? Oh, you guys are getting it already. You don't need me anymore. You're right, it's A. So we're testing if nothing's going on, right? Our null hypothesis here that we're going to test is going to be that our value should be equal to 0, just like we had for chi-square, right? So we're going to see how far that value gets away from 0 to whether or not we have statistical significance. And we can have the software do it as well. So again, that's our H0, H0, null hypothesis, rho is equal to 0. Alternative, it's not equal to 0. There's some kind of correlation going on. So that's the test that we're going to do. We're going to compare it now to another table. We've gone through all the tables. We did the T table, the F table, and here's on page 418, and also in this little cheat document I made for you of the tables. Now we're looking at the critical values of R. So at our significance level of 0.5, usually we're looking at this one, depending on the degrees of freedom. And for correlation, it's going to be n-2 because we're correlating two variables here. So it'll be n-2. And again, we're going to do the same thing. I'm a broken record. We're going to compare that test statistic to this table value. If the test statistic is greater than, we're going to reject our null hypothesis. We have a significant result. So the distribution for our correlation, as far as our theoretical distribution, it's going to be centered on 0, right? Because the correlation should be 0. And the sampling distribution is approximately normal. That's what we're kind of figuring out here. So in the null hypothesis, that rho value should be 0. We have assumptions, just like with every test, and requirements. For correlation, we're making the assumption that the scores on X are normally distributed for each value of Y as we do a correlation. And if we also assume that for both variables, they're homoscedastic for each value of X, the variability of Y is about the same. Homoscedasticity is kind of a big word, but basically it means as we look at, let me pull up a graph here. If you look at chapter 9 where you're doing a correlation, so, and we're going to do this one as an example, these test scores. So we say if you get a certain score on the final or the midterm, you're going to get a certain score on the midterm, you're going to get a certain score on the final. So we assume that the better people do in a midterm, right, the better they'll do on the final. And so we correlate these two. And homoscedasticity means, well, we measured people at 3, but what if someone got a 3.5 out of 10 on the midterm? Well, we're kind of in the middle. We don't really have that data. We're assuming the points between here are homoscedastic. That means that we assume that the variation is going to be the same between those 2 points. Another way to think about it is, in a broader sense, carbon-14 dating, because I used to teach chemistry, right? So carbon-14, gosh, the half-life is, I don't know what, 7,000 years? I have to look it up. It's a long time. Students always ask me, were you alive 14,000 years ago and watched 2 half-lives go by? Well, I'm not that old, right? So we assume that over time, carbon-14 is going to decay. If we watch it for 24 hours or for 2 weeks, we can assume for 100 years it's going to decay the same. So that's what we're assuming with correlation, that these values of X and Y are not going to vary too much throughout their lifetime. And again, our significance, we're going to compare that value of R, the correlation value, to our table at, as I said, n-2 degrees of freedom, because we have 2 variables, 2 mathematical principles we're looking at here. The magnitude of the effect, remember, we talked briefly about this, the R squared. The R squared tells us the magnitude of how tightly those 2 are correlated. And it's something we call R squared. It has 2 names, really, just to confuse you in statistics. It's called coefficient of determination. It's also referred to as the proportion of variability in one variable with or explained by variability in the other. So both X and Y tend to vary, and the correlation, if we square it, it tells us the proportion of one variable that is shared by or explained by the variability in the other. So both vary, but variation of one helps to explain the variation in another. And it's kind of like the eta squared we had for our ANOVA when we compared the errors that we see between the groups and within the groups, right? It's the same kind of argument mathematically. So R can be affected by a lot of things, the restricted ranges of values. So if you have a restricted range, so say you only measured people between getting a 4 and a 5 or a 4 and a 6 in the midterm, it can affect your correlation. Extremes distributions can affect your correlation, outliers. So if something is really outside the realm or it's an outlier, it'll affect the correlation. And also how we measure stuff as well can affect correlation. So we have to look at that when we're correlating variables. So regression is probably something you've heard about. You guys probably did all of this back in high school math and forgot it, because who uses high school math at their job these days, unless you're an actuary or something. But regression is something you've heard of before, or regress to the mean means that it's a technique by which we predict using our data. Once we get our line, which we'll talk about in just a bit, right? We've made this least squares line, you probably remember from math class. We can kind of predict based on certain values of X what we're going to get for Y. We may not always be right, but we can kind of predict, hey, if someone gets a certain score in the midterm, they're going to get a certain score in the final. So there's a strong link between correlation and regression. So when we do regression, we put the dependent variable, or our outcome this week, is going to go on the y-axis. We're going to try to predict the y given x. So x is sort of our independent variable, our predictor variable. It's not quite as easy or clear in correlation, because some things just correlate. One's not really predicting the other. They just share a correlation. But our outcome, we want to put as much as possible on our y-axis. So again, we're going to predict values of y based upon our values of x. So to do that, we do what's called linear regression. This works well for stuff that follow a linear model. So again, this course is Intro to Statistics. We're going to keep it as basic as we can. We're going to look at things that have linear correlations. So we give a drug to a patient. Typically drugs we give, if we do a dosing curve, the more drug we give, the higher the dose that will be in the bloodstream. The more cholesterol drug we give, we'll probably see a reduction in cholesterol. So we see a correlation, and typically these are done for linear correlations. And this is the equation of the line. So in math class, you probably remember, right? In math class, we call it y equals mx plus b. But just to confuse you, in statistics, we say it's y equals a plus bx. The y, that's the outcome variable, is going to be equal to a, which is our intercept constant. That's the point, well, here comes the math, right, at which the line crosses where x equals 0. So that's where it crosses the y-axis, right, where x equals 0. That's our a value, our intercept, plus b is going to be the slope of the line, and then x is our x values. So y equals mx plus b from math, you probably remember, is y equals a plus bx in statistics. So when we get that equation from the line, and you did this in math class, or you had your calculator did it, some calculators, my handy dandy TI-30X actually can do it, can make a linear regression, or we'll have the computer do it tonight. StatCrunch can do it. Once we get that line, then we can take that equation, once we solve for the equation of the line, and you probably did this in math class, right? To solve that, it's rise over run, change of x over change of y. Too much math tonight, but that's the math behind the statistics here. So again, we'll have our a, or intercept, and then we can put in values of x, and we can predict values of y. That slope is called the regression coefficient. And again, that is a big math solving, but we'll make the computer do that. So to do this work, and if you've read through this chapter, as you read through chapter 9, some of this will make sense. This is the math, right? So here's our midterm score, there's our final score. And you can kind of see if they got a 2, they got a 3 in the final. They got a 6 in the midterm, they got a 7 in the final. The software is doing all these calculations, and it's going to make that least squares line. So it's calculating, we have to calculate the means, here we go. The deviation from the means, here we go. Cross products of the deviations, there's our x, y. So we're going to actually multiply them, and scores from their respective means. All of this looks this way. So this is the data from the textbook example. We'll do some more as well tonight. But again, here's our midterm scores, and we're predicting our final scores, our outcome scores. So the correlation here is pretty tight, right? 0.955. So remember, our values vary from 1 to -1, and this is a positive correlation. So the higher the midterm score, the higher the final score. That makes sense. And this is our regression equation once we solve that equation of the line. Again, the points fall along the line pretty strong here. So this is a pretty strong correlation, right? 0.95. We've got a very strong correlation. Here's our slope, so it's almost 1, it's pretty linear. And again, the higher the midterm score, the higher the final score. There's our A, 1.5. That's where the line crosses the y-axis where x equals 0. So again, we're doing all the math here, right? We're just taking the score. Say we have a value of 1 for x, then we have the actual score that the person got. So here's our value of 1 here. Their final score was actually a 2. And by our line, we predicted it should be different from that, though. They should have gotten about a 2.4 or something from the line. So we would predict that score should be a little higher, and then we get an error from that. So we generate errors based upon this series of how we're drawing this line. And this is the difference of that is between the actual and predicted is the residuals, or E. So this little E value here that we get is the difference between what we predict and what actually happens. And of course, to draw the line, what we do is we try to make these as small as possible. So the math gets a little crazy, but what we do is we square those residuals so that make all the negatives positive, right? We get all these positive values, and we draw the line, or the computer does, or the calculator, such that all these residuals squared are going to be as small as they can. So we draw that line as small as we can. So this is all the math that the computer is doing. And if you want to think about it, so in a way, here's our line here, right? Here's our average for our outcome. Our average for the y was 6, right? Let me grab the cursor here. So here's our total. So we take the average of the outcome, the mean, and then we compare each value to that. So that's the largest one for our total. And that's our 60 that we get. And we'll see the software calculating this as well. But this is how we can do it by hand. Look, so you can add them all up. Dr. Palit did this in the text. Or you can look at what's termed the model here. And the model is looking at the regression model. It's the estimated value, the regress value minus the mean. So this is comparing it to our average outcome. And then the error is the smallest one, the 5.28. The error is basically the distance between the actual and the estimated value. So the little green spots here. And that adds up to our 5.28. So this is all the math that the computer is doing. So again, the standard error of the estimate is, in this case, is the index of how wrong on average our predicted value of y is. The software is going to calculate this for us. And again, the larger the correlation coefficient between the two variables, right, the larger the R, the smaller that SE, the standard error, is going to become. Just like we had for when we were looking at our averages and means from the test we've done before. And then the proportion of variability, once we have the R squared, that tells us how tightly correlated they are, but it doesn't explain everything, right? So there's something left as well when we look at that. And what's left over, the 1 minus R squared, is whatever is, could be the phase of the moon. It could be someone taking a exercise regimen, affects their cholesterol, whatever else is not in there, that's our 1 minus R squared. And we'll see some more examples of that as we go along. So again, we can do this one pretty easily by just hitting our simple linear regression in StatCrunch. So we can put those values in, and then it'll spit out the answer for us. So again, we can quickly get StatCrunch to do this one. Again, midterm and final, 5, 9, 7, 9, 3, 4, 1, 4. So we've got 10 subjects, and our final scores were 3, 7, 6, 8, 9. 9 got a 10, 4, 6, 2, and a 5. So we can pop those into StatCrunch, click on that Stat tab. Again, we can go to our regression. We can also get it from the summary stats, can give us the correlation. Or we can do the linear regression right from our regression and click on simple linear, and it'll do everything for us. So again, the X variable is going to be our midterm. Our Y variables are outcome. We want to know how they're going to do in the final. Again, there's a hypothesis test. So for this one, just like with chi-square, the software is smart, right? With the one sample t-test, we had to put a population value in here, but here we're going to keep it as 0. And then we click compute. So it's going to do all of that math for us. If we do the regression model, we click this little arrow here, it automatically plots it for us. StatCrunch does this thing that Excel doesn't do. If you graph in Excel, it takes the data and fits it, all the data points, into what it's displaying. If you want to really see the differences, you click down on this little contextual menu here and click the x-axis. You can put it at 0. We want to see where that A value comes from. Click again for the y-axis, put that one to 0. And now we can see where that value goes. And I can, as I drag over this, it tells me the equation of the line as I go through it. And you can see right here, the intercept is at about 1.5 or so, 1.6 is happening right here. We can get all those values from StatCrunch. What we're looking at is not the intercept, we're looking at the p-value for the slope and for this regression model. So this is where it's comparing, here's the 8 degrees of freedom, n minus 2. And again, here's our 5.28. So if you pop to the next slide, I'll bring this one back. There's our 5.28. So StatCrunch did all the math here. 60 is the total, right? That was the difference between, you take everything and do the total, that's 60, right? That was adding them all up and comparing that to our, the mean, the output Y, the final exam score was 60. So it's doing all of this math, and then just like it did for ANOVA, it calculated this F score, the 82.91. And again, if we do that, we just take the mean squares for the regression or the model. So 54.72 divided by 0.6599, and we get our 82.92. So I get the same answer on my calculator, just like we did for the ANOVA. It's doing all of that math for us. And again, we're looking at this p-value from this regression model that we're looking at. We tend to not to look at the intercept, although we can, but we're really looking at the slope of the line to see the correlation value from this F statistic that we're looking at. So again, when we look at the output, either way here, I've got both. It looks like I did it right. So there's our R squared value, right? Because we take 0.95499 and I square it, I get the 0.912. Okay, so it's just doing the R squared here from the correlation. And there's our sample size. That's where we get the n minus 2 from. There's our error, 8 from the model there. And there's our equation of the line, y equals a, 1.51, the intercept, plus 0.897 is the slope, and then there's the x value, the midterm, y equals a plus bx. So the software does all that work for us, again, based upon how we did all the math, right? So it's doing the same thing. So let's do another one. So let's look at one where, another one we type in, and we'll do this one together. So what if we take the dose, we give 10 test patients. So again, I'll go back to my StatCrunch, open up another sheet here. We have a dosage and hours of relief. So dosage, and we'll call it relief, hours or relief time. So again, whether we load the data in or we type it in, copy and paste, we've got a lot of ways of getting data into StatCrunch. So again, you can pause this recording later when it's available. Make sure you can do all this. There's practice ones to do on the discussion threads. So type this one in now, follow along, or do it later when you have time. Watch me here, hopefully I won't make a mistake. 22, 18.3, 24.5, 22.7. So it looks like the more dose of the drug, we're getting more relief. So we want to know, what's the correlation R? What does it mean in this case? What is the coefficient of determination? What does it mean? Is there statistically significant correlation? So you know it's coming. Just like last week, we'll ask that question. And then we're going to look at predicted value for someone who took 2.5 milligrams of the medication. We can go ahead and go right to the Stat tab. We can do the regression. So we're working all the way down the table here, just above ANOVA. We've got, again, simple linear we'll do in this course. We've got X and Y. So what is our independent variable here? It's going to be our predictor. What's our independent variable, the dosage or the relief time? What's our independent variable going to be that we'll put in the X? Dosage or relief time? Yeah, you guys got it. So you don't need me anymore. I even mixed it up because usually I ask you the outcome variable and you still got it right. Okay, so dosage goes there and relief time is our outcome that will go in the Y. You guys are pros. Okay, so we put that in there. We leave our test alone because that's our R equals 0 that you told me from the beginning is right. Then we click on compute and we get our results. Who can be the first to type in? You know it's coming. With a p-value of 0.002, so that's 0.2%. Yes, significant, no, not significant. With a 0.2% p-value, F statistic's pretty high, 40. Yes, this one's significant. Correct. And there's our F statistics, which is very high, but we can compare this to the R value. The correlation coefficient is 0.914. We have 10 sample size n-2. Who can be the first to type in at 10, let's see, 8 degrees of freedom, n-2. What's going to be our critical value in the table? We compare to R, 0.914. With 8 degrees of freedom, what do we compare to? At 5%, 0.632, right. So we go to n-2, n-2, we've got sample size of 10, we go along to 8, 0.632. Notice that the R is at 0.914. And it's significant. Again, the test statistic, absolute value of the test statistic is greater than the tabled value, further telling us we have a significant result and our p-value is below 0.05. Perfect. So we've got a correlation. Click a little arrow here, or we could have gone to scatter plot and made our plot. There's our plot and our dosage. If we want, we can click on these and put them at 0 so we can see that axis tell us the A, and notice this little negative 0.9. Yep, it'll cross right about here, 0.9. So there's our intercept, and the data is a little scattered, but it's still pretty linear. I mean, it's falling pretty close along that line. So it's about 0.91, fairly strong correlation. Again, positive is values of X increase, values of Y increase, right? And we did the significance. Let's look at if someone takes a 2.5 milligrams of medication. So to do that, here's 3. Now notice from our data set, let me move this over again. We didn't have anybody dosed at 2.3. The lowest dose we had was 3. So we're making an assumption, right? That homoscedasticity, we're assuming that this is going to be the same all along this line. For all values of X, values of Y are going to be the same. So 2.5, so here's 3. First, we're going to eyeball it from the graph, right? Here's about 2.5. So it looks like it should be intercepting right about here on our line. So it should be 5, maybe 6. Should be the hours of relief based upon our graph. But we can have the software calculate it. If I go to options, I'm going to edit this. I can go down to this one. And we can put in predicted values of prediction of Y. Here we go. We can type in an X value, and that would be our 2.5. So again, I'm down here with predictions of Y, right underneath the hypothesis test and confidence intervals. And I click compute from that, and we'll get another, if I scroll down, there it is, 6. And again, it matches what we would predict from looking at the curve. Okay, and again, I got a YouTube video on this. I think I did the fidgeting example if you need another one, but pretty simple. We did a lot of this in week 1, but now we're just taking a step further and we're looking at the p-value here, the equation of the line, everything is typed out for us, sample size R squared, right? The coefficient of determinations right here. So that means the R squared, right? We square this value, take 0.91 and square it in your handy dandy calculator. 84% of the variation in the dosage accounts for the variability in relief time. What does that mean? Well, that's pretty good, but there's what, another 84, 16%, could be their meditation, could be they're taking essential oil, maybe there's something else that's affecting their relief time, but almost 84% of it is accounted for by the dosage of the drug. So there's typing. Let's do a loading data. For this week's discussion board, you're looking at age and optimism score. So let's look at age and cognitive score. So another one in that page, and I think I've got that open on my desktop. So this is the week 3 discussion question 2 data. So for the discussion board, people are already posting to discussion board practice example. We're going to look at age and, oh, this was from week 3. So this one we did chi-square on. And for this example, let's look at cognitive score. And I think the other discussion thread, let me check that one. But this week, so there's a cholesterol example to put in, like we just did, put the data in. And then, oh, for this discussion thread is week 2 discussion data, you're going to look at age and optimism score. And let's look at, from week 3 discussion question 2, we'll look at age and cognition score. So let's load that one in as an example. So we typed one in. Let's do one from the file. Click upload. So this is one we worked on last week, and we're going to look at age and the cognitive score, GP, General Practitioner Cognitive Score, that we looked at last week. Week 2, we may have done that one. To look at age and cognitive score, again, we would hit the Stat tab, Regression, Simple Linear. We're assuming we're going to have a linear outcome here. And for this one, what's going to be, let's try the Y first. I'm going to try to mess you up. What's our dependent variable? Their age or their cognitive score? What's our outcome here? Who can type in? Would it be their age as the outcome or their cognitive score? What are we interested in the dependent variable and why? Yeah, you guys don't need me anymore, you're pros. Good. That's our dependent variable, our outcome, cognitive score, and then we'll put the age in. Again, we'll leave our test alone, and we'll click compute. So when we do regression that way, if we click the little arrow, it's going to give us the graph. And we've got quite a scatter here for age and cognitive score, but oh, it's not looking good. As you get older, your cognitive score would go down. So this one's a negative correlation. So we should see a negative R there, and we do. And 50.5, not too strong, but it's pretty well correlated. It can be spread out, but it's got a medium type correlation. R squared here is 0.30, so 30% of your cognitive score, the variability in your cognitive score is accounted for by the variability in your age. So that's good news. That means 70%, we could exercise, we could do crossword puzzles. There's 70% of something else is influencing that cognitive score. You know what's coming. The F-stat's pretty high. We've got a p-value of less than 0.01%. Yes, significant. No, not significant. With a p-value of 0.01%. Yeah, significant. Everybody's getting it. Good job. This is significant. Now, you know what's coming next? Let me pull that table up. 400 people in this study. So n-1, there's our sample size 400. So we're going to be down here past 300. What do we compare the R value to? The absolute value, 0.54. So we're past 400, we're almost to 500, 0.113. Again, we could Google the table if we wanted to get more clear, but we're only about 0.21 away from each other here. And you can see the absolute value, 0.54, is greater than our 0.113, even at 300 degrees of freedom. So again, our value we compare in our table. The test statistic is greater than that, significant result. We've got our graph, which we could have done from the scatter plot, right? We could have gone to our StatCrunch and hit the graph and scatter plot. But when we do regression, it does it automatically for us. graphs it. So there's the significance. So we did the R value. Coefficient of determination here was about 30%, the proportion of variability. Significance we did. So even if there's a smaller effect or it's a little less correlated, it still can be significant, right? So even some drugs we give patients, you know, the data may not be as well correlated, but if it's significant, that will help our patients, right? It'll reduce cholesterol, or here it'll predict their cognitive score. So what's the prediction for a person who's 85? Again, we can eyeball it from the curve, from the graph rather. So there's 85 years of age. Where it strikes that line, looks like the cognitive score would be about 5, probably a little less than 5. We can get the software to calculate it. We can just click Edit and go down to our prediction of Y. We put in our 85-year-old, click Compute, scroll down here a little bit, should be around 5, yeah, 5.1. So we can estimate it from that graph to make sure we're getting the right answer, and then have the software calculate it. So the Montreal study, for the assignment, you're going to look at the PANAS score and age, and we can even load in this one from the Montreal mental state study. I'll drop and drag that one. So again, this one's for the assignment. I'll upload that one. So again, whether we type the data in, we can load it in, we can copy and paste it in. So for this one, this is the PANAS score. This is the positive negative affect score. I actually use this with my veterans when I do my horse therapy with them. It's a score between 1 and 5, 0 and 5 rather, that tells us the affect of the subject, the higher being a better affect for things like feeling good, feeling excited, feeling honest, feeling energetic. And then the MST score is a mental state score. The higher that one is, the better mental state they're in. So for the assignment, you're going to correlate age and PANAS score. So for an example, let's run one with age and the mental state score. Again, we're going to find that R, the R squared, what it means, and we'll see the significance. So let's do that one again. We just hit the Stat tab, regression, simple linear. And again, what's going to be our outcome here? Is it going to be their age or their mental state score? What's our dependent variable going to be? Yeah, people are typing mental state. Looks like you got it right. Okay, so we'll click, that's going to be Y. MST score, our X, our predictor is going to be age. And I don't think the news is going to be good for me, but we'll see. I'm 55, we'll see how bad it gets. There's our graph. Oh, this was a young study, so I'm not even on the graph. I'm safe for now. Hey, it looks good. At the older you get, your mental score, your mental state seems to improve. It goes up. Good news. Here we go. So there's our 0.072. So this one's not as well correlated. You can see there's a lot of scatter here in the data, but we're getting a correlation, and this is the R squared is so we square that 0.005. So only about 0.5% of your mental state score is accounted for. The variability in your score is accounted for the variability in your age. This is a real weak predictor, although it's positive. And who can be the first to type in with a p-value? We're going to look at this one, the slope, or on our model at n-2 degrees of freedom. 42%, no, significant, yes, significant, with a p-value of 42%. People are typing no, yes, no, this one's not significant, right? Because we're way above our 0.05. Okay, good job on that one. Oh, you know what's coming? Let's go to the graph. Where's our degrees of freedom? At 125, n-2, 123, 123. So what do we compare the value to here? With our R of 0.07, what's the critical value from the table for this one? Anyone see that one? So here we are at 123, 125. So it should be about 0.195, 0.174. Either way, around that level of our 123, we're going to have a non-significant result. This one is less than that critical value for R, right? Yeah, I would compare it to the 0.174 here. 123, 123 is very close to 125 degrees of freedom. Okay, and then someone 23 years old. We can look on the graph. It should be, their score should be about 2, right? That's where it intersects the line. Not quite 2. And then we can get the software. Again, if we click options, we can redo it. Scroll down, predicted value 23 for the age, for the X. Click compute. Yeah, 1.98. It'll calculate that outcome value for us. So that's as difficult as regression gets. And just with this slide, if you want to review page 35 in Polite, we talked a little bit about this when we did descriptive statistics. But when we're labeling charts, we want to primarily keep the data where the points are. We want to have clear labeling for the X and Y axis. And again, we can go to edit and we can, like we did, change the display description. We can change the fonts, make them a little larger or smaller. Like we went over in week 1, we can do that and just hit refresh. We can make them a little bit better. So graphs, and StatCrunch does most of this for us. So our graphs should look good. They should have a title. It's good to put a title on. Make sure that you've got the axes labeled and that you can read the X and Y axis. Okay, so that's regression. And again, we did most of that in week 1, but now we're just going through and analyzing the data. Again, getting StatCrunch to do the numbers for us. And we can do that whether we type things in or whether we take them from our Excel sheets. Now, the rest, multiple regression, I'm kind of just gonna, if you're watching the recording, this is where the course kind of stops. So I'm gonna go briefly over multiple regression, but we're not gonna do this type of analyses in this class, but I'm gonna go briefly over multiple regression and we'll end with a discussion of the other types of tests that are done. But we're not gonna be doing multiple regression in this course in StatCrunch, although I'll go through a quick example with you. And then there's just some calculations to be done for the homework assignment on multiple regression. But for the most part, we are going to stop our computations in StatCrunch here, but I'll go through some examples for you. Multiple variables, you can have a multivariate analysis is where you have at least 3 or more variables. So it's a little confusing. Don't confuse this with ANOVA, because ANOVA is analysis of variance where we have one variable with 3 or more groups, right? 3 or more groups. But now Elvis has left the building. We're talking about multiple variables, which largely we've not talked about in this class. It's a tool and it's an extension of simple regression. So you can now take multiple predictors and look at how it's affecting an outcome variable. It's a really powerful tool to looking at and understanding multiple variables. So it looks a little bit different. That predicted Y value, we still have our intercept, but then we have multiple variables, multiple predictors that can be used in multiple regression that's going to affect our predicted outcome. It modifies the equation somewhat. And this is all done by computer. So we can't even imagine to start doing this by hand where we add up try to find the averages and the means and the least squares, right? And the residuals. It's all done by computer. These coefficients are done when the other predictors in the equation, we can remove or add them and it changes those contributions. So it's a little more complicated analysis. When it calculates that correlation coefficient, the R value, it's going to take in all of those independent variables. They're taken together to determine the magnitude of the relationship. And again, the coefficient of determination, or the R squared, the magnitude, or the proportion of variance, right, is accounted for by all the predictors taken as a set. So it has very similar to a simple regression, but now we're using multiple variables to predict that outcome variable. And again, we have the same types of assumptions, very similar to what we had in linear regression. And again, this is all done on computers. So for example, if you go back to the course shell and course resources, I've given you in the shared documents area, again, we're in course resources, shared documents area, where I'm putting some of these data sets. There's data sets that I put here for the examples. So the ANOVA, an example. And what I'll do is I'll put one for the regression, but I'll go over that now and then I'll place that in the course shell too if you want to practice with that one. But again, we're not going to be doing these analyses in class. But if you look at chapter 10, this multiple regression, we'll just do one example tonight and then we'll stop. So this is table 10.1. This is multiple variables, right? Here's all of our independent variables, all of our x's. We're trying to predict the graduate GPA someone has in graduate school. We've got several predictors, not just one. We've got an undergraduate GPA, their GRE verbal, right? The graduate record exam that most universities have you take to get into graduate school. There's a verbal component of that exam, a quantitative component of that exam, and then there's something called a motivation score that the whoever took this data recorded. So there's 4 predictors for one outcome score. I mean, you can take the averages and you can start trying to get the residuals for these, but essentially the computer calculates a new equation of the line, a new y equals a plus bx. And there's our outcome or a y variable. Here's a, right, our intercept. And then these are all of the 4 components coming up from these independent variables. And what we do is once the computer calculates these contributions, then you can put in a value for x, you can put in a GPA score, put in the GRE scores for x2, x3, and x4, and then you can calculate the outcome. And StatCrunch will do this for us as well. Back to StatCrunch, and we can load this data in. And again, I've got it on my desktop. So again, I'll just do this one as an example. So here's all the data from chapter 10. So you can load these into StatCrunch and you can do multiple regression. On the Stat tab, you click regression and you just keep going. So here's multiple linear. You can select your outcome. So again, here our outcome is going to be the graduate GPA. We want to know how they're going to do in graduate school based upon the other 4 variables. So I'll hit control, undergraduate GPA, motivation score, their verbal and quant, and click compute. So it'll calculate and give you a p-value for each of these x variables. It'll calculate an F statistic, so it's going to look at those variables. And again, it's taking those mean squares. You just divide this by this and you'll get the F statistic. And then here's the outcome. So it spits out that long equation for you. So for example, I'll go back to this slide. So these are all the output that you see coming from the software. And if you go back to the textbook, then once you have the equation solved for you, you can then calculate this predicted value of y. So for example, here's our predicted value of y here. So all it did was, if you take the first one, so here's the first student, right? They got a 3.4 on as their undergraduate GPA. So you put that in there. There's the A value. Then that's the 0.762 is the slope or the beta weight that it calculated. So there's the undergraduate GPA. So you multiply that. And so you just add them all up. Here's the next one. For the GRE verbal score was 600. You put 600 in there times 0.013. That was the slope or the contribution from that one. There's the quant is actually subtracted. So you have to subtract this one. They got a 450. So you subtract that one, and then you add the last one, which is the 4th variable, the motivation score. And for the first one, again, it was 75. So you put that in there, do all the math, and you get 3.46. And that's their score. Their actual graduate GPA was 3.6, so it fell off a little bit on this one. But that's the predicted one, and then that's the actual score that they got. So very similar to linear regression, now you just add up all of these slopes, if you will, or the coefficients, and then you get your final value for y. All of these will allow you to use multiple regression to predict outcomes for your predicted value of y. Just a little different. So again, it calculates all of these regressions, tells you some of them are significant, some of them are not. Again, multiple variate analysis, a little bit more different than we've seen. And we can also check it too if we calculate what the software is doing. So there's our F statistic that I calculated. We can calculate that. So this is the formula from page 231 in the text. So that F value, again, similar to our ANOVA, where we looked at the variation between the groups and within the groups to get our F value. So here the F is going to be equal to the R squared. There's our R squared down here, the 0.8835 divided by K. That's the numerator. And the denominator, and the k is the number of predictive variables, so that's 4. So our r squared is going to be our 0.8835 divided by 4. So again, we're just doing the math here on this one. That's in the numerator. The denominator is going to be 1 minus r squared divided by n minus k minus 1. So 1 minus r squared is going to be 1 minus 0.8835 divided by n. So we had, our total was, we had 20 students. This is for our model, which is -1, but there was 20 that we looked at for the multiple regression. So n minus k minus 1 is 20 minus 4 minus 1. So this is all the math the software is doing. If you take 0.8835 divided by 4, I get 0.220875. 1 minus 0.8835 is 0.1165. I can do 20 minus 4 minus 1 is 15, right? So we keep going with our calculation of f. Boy, I hope I get the right answer after all this math. So I got to do the numerator first. 0.220875 divided by 0.1165 divided by 15, 0.00776667. So I got to keep that numerator straight first. 0.220875 divided by 0.00776667, 28.439. Well, close enough. I'll take that. So that's the calculation of f. Again, we can get it from just dividing the squares up here, but this is the equation. This is on page 231 of the text, but that's what the software is doing to get the f value. All right, that's enough math for one night, I say. I'm going to kind of stop there, but I'll describe the rest of the multivariate analysis, and those are in your little cheat sheet here as well. The one I told you, now that we're at the end of the course, we can look at all of them. These are the multivariate ones. So again, we talked a little bit about multiple correlation, and again, these are the SPSS commands, but you can see that we've got multiple variables here, 2 independent variables and 1 DV. So multiple regression is with multiple variables. The others are, you can read through chapter 11 where she talks about some of them. So there's NCOVA, so that's analysis of covariance, so that's this one. And again, for these, we're getting some what's called covariates. And covariates are some pre-intervention measure of an outcome, a measure of a confounding variable, something that might alter your outcomes. And again, these are multiple variables that we're looking at. The covariates are typically interval ratio. So now you see here's your covariates here. And once you get covariates, you know you're doing NCOVA. You don't do those in multiple correlation or multiple regression. You can have Manova, and Manova is another one where you've got multivariate analysis of variance. So here it's an extension of ANOVA. You're testing mean group differences on 2 or more dependent variables. So these are the other tests. For this course, we're not going to analyze any of these. You'll probably do those in another stat course if you take it. But just so you know, those are the other types of multiple variate tests that are available. And again, you can look at what's your independent variable, a covariate, that'll tell you which test to use. And also, again, our dependent variables are all interval ratio. And for our independent variables, they tend to be nominal or interval ratio for multiple regression or nominal for NCOVA. So these are the more advanced tests, again, multiple variates, not to be confused with our other tests that we do, like ANOVA. So those are up. The ANOVA is up on our other test. Now that we're done with the course, there's our ANOVA. We just have 2, right? Within our independent variable is nominal, so we have different groups. That's how we get to ANOVA, when we have 3 or more scores that we're looking at for our analysis of variance. That's it. Let me talk about the project at the end. So again, you've got your little cheat table to look at. That was a quick overview of multiple regression. Again, just like last week, start with the discussion threads. People are already posting up to those. This is our week 4. Practice with the discussion questions. Then for the assignment, I think we've gone through most of it. Discussion threads, assignment, final exam, the independent project. So we've done all of these now. So again, number 1, pick a variable. So here's the data. So in week 4, here's the data set. So just click on this one. So I did an example for you, right, that I put in course resources, and people have already looked at that one. But now you'll do this one. This one's got about 1,000 subjects in it. And now all throughout the course, I've been asking you, forcing you to pick the data that I want you to look at. So now you've got a whole list of variables to look at. Again, the code key is here, down at the bottom. The background of the study is here. This is data that Dr. Palit keeps sending me. Some of it's pretty obvious, but there's other stuff here in the code key if you're confused what they are. And you can see some of these are nominal level variables. Some are interval ratio level variables. There's lots of different stuff you can look at. So again, number 1, the bar graph, right, it's going to be nominal. And Taylor said, can we use different data from previous weeks? No, for this independent project, you have to use this data set. So pick one of these, and one that you want to look at, not one that we've done before. So this was the one I didn't want to show you in week 1 because you'd freak out, but now you guys are experts and you can do this huge data set now. So for the independent project, you want to use this data set. So again, number 1, the bar graph, remember, was nominal level data for bar graphs and pie charts, nominal level variables. Number 2, descriptives of a quantitative variable with an average, median, mean, right? Standard deviation, that one's got to be interval ratio. So number 2, you're going to do a histogram graph. Number 3, cross-tabulation. We did last week. We did week 1, but we did chi-square last week. So this one's the test would be chi-square. For cross-tabulation, again, is with nominal level variables. So cross-tabulate some 2 nominal level variables. Comparisons of 2 groups within a single variable. So appropriate test. So this one's going to be our 2 sample t-test. And remember, if there's no 2 groups, you're going to have to split the data, just like we did in week 2. So this one's a 2 sample t-test. Number 4. Number 5, 3 or more groups, right? That's our ANOVA. And number 6 we did tonight with a scatter plot and correlation. And now this one you can do with 2 interval ratio variables. We've got a bunch here to do. And you can correlate them. And again, do the appropriate test for that one as well that we went over tonight. Make sure you choose the right variable. So all throughout the class, I've been forcing you to analyze data. I know it's been horrible. But now pick something in here you're interested in. You know, look at poverty, education, doctor visits, ethnicity. There's cocaine use, marijuana use. There's physical health scores. There's the MES score, which is the multi-factor emotional intelligence score. So pick something of interest to you. When you finish this project, keep it. You know, it could be handy for you to look over. You never know when you're going to do stats again, or if you're in a job interview, because now that you've got the course done, you can add StatCrunch to your resume. You are all proficient in using software. And so keep that project, keep a snippet of the data to remind you of what you analyzed. And then you can discuss that in a job interview or a grad school interview. Statistics is always going to help you. So make sure you choose the right variable. So we've been doing that all throughout the course. Short descriptive statement, the meaning of the results, right? And for that is how I'm going to grade. Right variable for each one you'll get points for, appropriate result in test or display, and description of the result. And then again, 2 points for overall, make the graphs look good, make them very readable. And again, look at the example that I did in another data set. I took a dose of my own medicine and did that for students. People found that helpful. And again, I used that as a template, put your data in. Like I said, I do that for my writing as well. I use templates all the time, put in the new data, just gives me a template to work from to get the work done. So you have the, again, discussion threads, the assignment, the final exam for this week, no quiz, just a final exam, independent project, start practicing on the discussion boards, put your work up, and again, you can correct it, just post another thread if you make a mistake, assignment, final exam, and final project. I hope this course was helpful. Everyone did well tonight. Good work, everyone. I hope this course was helpful. I hope that you all learned something. I know statistics is not everybody's favorite subject, but it's very important. I've used it all through my career, all through graduate school, and I hope that this was helpful to you. Great, you guys are welcome. And I'll go ahead and stop the recording there.